Today, it is no surprise that all stars in the universe are born in vast, cold clouds of gas and dust drifting through space. Under the influence of their own gravity, these clouds contract and heat up, igniting nuclear fusion. However, we often forget that most stars are not born in isolation. These clouds can be so massive that they contain thousands or even hundreds of thousands of dense regions that will eventually shine as new stars. Once, our Sun also went through this stage. It was born and later left its parent cloud. The details of this process remain elusive to astronomers, despite the Sun being the most studied star in the universe. Where and under what conditions was it born? In what environment? And how did all this influence the emergence of life on our planet? Scientists hope to answer these questions by searching for the Sun's lost siblings. These stars, along with our Sun, once left their cradle and are now scattered across the galaxy's disk, amidst hundreds of billions of other stars. The idea of finding the Sun's relatives is intriguing, but it becomes even more fascinating when we consider these stars as potential homes for rocky exoplanets. These planets may have formed under similar conditions and with the same chemical composition as our Earth, the only known planet that harbors life. So, how do astronomers search for the Sun's lost brothers and sisters? Although the exact details are still unknown, astronomers have a general idea of how the Sun was born based on observations of nebulae. The term nebula comes from the Latin word for cloud, and each nebula is indeed a cloud, primarily of hydrogen and helium with a small fraction of other elements. Some nebulae are dark and obstruct our view of distant stars in the Milky Way. Others are very bright, serving as star-forming regions within the galaxy. At least one nebula is visible to the naked eye, even without the aid of telescopes or binoculars, despite being over 1,300 light-years away. This is the Orion Nebula, home to 700 stars at various stages of formation and part of a much larger structure known as the Orion Molecular Cloud. It is a dynamic region where intense radiation from massive stars heats the surrounding gas and blows it into space. As a result, such regions are short-lived compared to other astronomical objects. In just a few 100,000 years, the Orion Nebula may cease to exist. However, it will leave behind something remarkable: stars and a young open cluster of bright blue stars. The legendary Pleiades are a perfect example of such a cluster, which is also visible to the naked eye. This young cluster, approximately 100 million years old, contains over 1,000 known stars, but only a handful are visible without optical aids. These hot, young giants, just a few million years old, serve as compelling evidence that stars usually form in clusters, with hundreds or even thousands of companions. Infrared studies of our galaxy conducted over the past 20 years confirm this. Between 80% and 90% of the stars in the Milky Way likely formed in clusters with over 100 members. Of course, there are smaller and less massive clouds, like the dark nebula Barnard 68. This nebula is often mistaken for the Void of Boötes, but is, in fact, a dark cloud with twice the mass of the Sun. What makes it fascinating is that it is on the brink of gravitational collapse and will likely begin condensing into a protostar within the next 200,000 years. So how do we know that the Sun wasn't born from a relatively small cloud, essentially in isolation? We don't know for sure, but there are several important clues, with the most compelling evidence found right here on Earth. The composition of chondritic meteorites, largely unchanged since the formation of the solar system, provides a unique window into the conditions under which our planet and system formed. Scientists analyze the chemical composition of these ancient space rocks, specifically looking for decay products of certain radioactive isotopes, such as aluminum-26 and iron-60. These isotopes cannot be synthesized by the Sun or similar stars. Their creation requires much larger and more powerful stars. Aluminum-26 is produced during the life cycles of massive blue and blue-white giants, while iron-60 originates from supernova explosions. By carefully measuring the concentrations of these isotopes in the early solar system, researchers can determine how close our Sun was to massive, powerful stars. These radionuclides could not have been part of the original molecular cloud since they have very short half-lives, lasting only about 1 million years. The fact that they are present in the solar system's material suggests that their sources must have been nearby, as our star system was still forming. This means that at least one giant star must have been close to the Sun during its early development, implying that the Sun was not born in isolation. Moreover, stars massive enough to go supernova are relatively rare in our galaxy. There is approximately one giant star for every few hundred solar mass stars. Thus, the Sun's birthplace must have been crowded, hosting at least several hundred other stars, and likely experienced at least one supernova explosion. This suggests that our stellar nursery resembled the Orion Nebula far more than a small cloud like Barnard 68. Massive stars of spectral types O and B have very short lifespans, measured in millions of years, meaning clusters that include such stars tend to dissolve relatively quickly. However, stars like the Sun, with lifespans of billions of years, eventually drift apart to wander the galaxy's disk individually. The gradual dispersion of the Sun's parent cluster began within the first few million years of its formation. The gas whose gravity held the cluster together heated up and dissipated, leaving the stars unbound. Gravitational interactions with other stars in the Milky Way and with massive gas and dust clouds further pulled them in different directions. Over a few 100 million years, the once dense stellar cluster became a loose association, stretching further apart over time. Eventually, the stars drifted so far from each other that it became impossible to visually identify them as originating from the same cluster. An excellent example of this process can be observed in the constellation Ursa Major. The brightest part of this constellation, the Big Dipper, consists of 7 prominent stars, 5 of which belong to the closest moving group to the Sun. These stars travel in roughly the same direction, have similar speeds, and share a comparable age. Once part of a loose stellar cluster, they now span tens of light years across space. Members of this moving group are no older than 300 million years, but the Sun and its close relatives are over 4.5 billion years old. Over that time, our star has completed more than 20 orbits around the center of the galaxy. Thus, if you assume that nearby neighbors like Alpha Centauri or Barnard Star are the Sun's siblings, that is not the case. The true siblings of the Sun may be located on the opposite side of the galaxy. So how can we determine what happened to the Sun's siblings, and have we managed to identify even one of them? Spoiler: yes, astronomers have identified at least one solar sibling. But how was it discovered? The odds of finding any member of the Sun's birth cluster relatively close by are not very high. Astronomers estimate that within a radius of about 300 light-years, there might only be a few solar siblings, assuming the Sun's birth cluster contained at least 1,000 stars. If the cluster had more members, the chances of identifying a sibling increase accordingly. Today, scientists are fairly confident that the Sun's birth cluster was not exceptionally large. In massive, densely packed clusters, stars tend to be close together, which can destabilize planetary systems around them. The fact that the solar system has distant planets like Uranus and Neptune, as well as even more remote objects in the Kuiper Belt, suggests that no other stars approached us closely in the early solar system. In a dense cluster, the frequent close encounters with massive stars could strip away protoplanetary disks from neighboring stars. For instance, there is evidence of a young star that was unlucky enough to be near an O-type giant. The intense radiation from the giant mercilessly destroyed the disk of gas and dust around the young star, a disk that could have otherwise formed planets and moons. Thus, the Sun likely formed in a moderately sized cluster, not too small, but not too large either. The chemical signatures of massive blue giants are present in the early solar system's composition, suggesting some massive stars were nearby. The cluster likely contained anywhere from a few hundred to a few thousand stars. This means that some members of the Sun's birth cluster could still be relatively close, within a few hundred light-years. It is no secret that the best marker of stellar similarity is their chemical composition. Each molecular cloud has its own unique chemical makeup, which depends on its age as well as its location in the galaxy. This is like a cosmic DNA that stars inherit when they are born from molecular clouds. The concentration of chemical elements heavier than helium, which astronomers simply call metals, usually varies from star to star. But this is not the case for stars born from the same cloud. The Sun has a slightly higher metallicity compared to its neighbors, indicating its different origin. For a long time, the Sun's parent cluster was thought to be the star cluster M67, which contains over 100 stars similar to the Sun and with a comparable metallicity. However, the Sun's orbital properties and those of M67 demonstrate that they have never crossed paths. In other words, The Sun could not have been inside the M67 cluster, a conclusion also confirmed by the Gaia spacecraft. This spacecraft provides the most accurate measurements of distances to stars and their relative motions in the galaxy. Thus, astronomers searching for the Sun's relatives use a combination of two methods. First, they identify candidates based on their orbits, modeling the probable positions of stars in the past. Second, they determine the chemical composition of these candidates using their spectra. Regarding the first method, it has certain limitations. Essentially, it is impossible to precisely know the Sun's position in the galaxy and how it orbited in the past, partly because there is still no exact map of the Milky Way. Moreover, our star may not have always followed its current orbit, as its metallicity suggests it was born somewhat closer to the galactic center and later migrated to a wider orbit. Additionally, there is always the possibility that, during its movement, the Sun passed near massive clusters or molecular clouds that could have gravitationally altered its orbit. Clearly, modeling all of this is very challenging. Therefore, astronomers typically select candidates based on similar orbital parameters and then rely on spectroscopy to identify our solar siblings. However, even chemical composition is not a perfect indicator. While molecular clouds do differ from one another, these differences can sometimes be subtle. They may be quite similar in chemical makeup. Moreover, stars can undergo slight chemical changes throughout their lifetimes. For example, differences can be observed between stars in the main sequence stage, those experiencing youth and middle age, and subgiant stars nearing the end of their life cycles. Thus, this must be taken into account in the models, or the search should focus on stars that are at the same evolutionary stage. As of today, only one star seems to meet all the criteria for both chemical composition and orbit, HD 162826. It is located 110 light-years away from us in the constellation Hercules, and it is not a twin of the Sun. But relatives don't have to be twins, do they? Stars can form from the same cloud yet differ in mass, luminosity, or temperature. However, they must be similar in age and metallicity. HD 162826 is 15% more massive than the Sun and is not visible to the naked eye, but it can easily be observed with binoculars or a small telescope, using the bright star Vega as a guide. In 2014, it was selected from among 30 other candidates identified by other research groups based on their dynamics and chemical composition. All these observations were conducted using high-resolution spectroscopy to gain a detailed understanding of the chemical composition. Astronomers specifically looked for similarities in the concentration of barium relative to iron, a metric that varies significantly between stars, even when they show high similarity in other components. Among all candidates, only HD 162826 turned out to be the best and the sole candidate fully qualifying as the Sun's sibling. In 2018, another interesting star was discovered in the constellation Pavo in the southern hemisphere, and for nearly a year, it was considered a potential sibling of our Sun. However, in 2019, after its galactic orbit was reviewed, this idea had to be abandoned. Nevertheless, considering that the Sun's parent cluster is scattered across the galaxy, finding even one representative is a significant success. Interestingly, the only known sibling of our Sun had been closely observed long before it gained this status. Another team of astronomers included it in their search for exoplanets. As of now, it can be confidently stated that no gas giants with Jupiter's mass orbit this solar sibling. However, the possibility of Earth-like planets has not been ruled out. These will be the focus of more powerful telescopes of the future, equipped with the necessary sensitivity. This is fascinating, especially if we assume that dense clusters of stars might facilitate better exchange of material between planetary systems. Objects like Oumuamua and Borisov's comet have confirmed that bodies from different stellar systems can indeed enter others. Could they serve as vehicles for interstellar panspermia, the transfer of life? While the idea is exciting, it is extremely unlikely. The reason is that interstellar objects, before becoming interstellar, may orbit their own system for tens of millions of years. Then, they could spend equally long periods traveling through interstellar space, exposed to cosmic rays. By the time these objects reach any planet in another stellar system, it is highly improbable that they would still contain viable microorganisms. But even if we assume that such objects could still carry life, what are the chances that they would land on a rocky planet similar to Earth? In young star clusters, where planetary systems are relatively close to each other and where the relative velocities of stars are low, the transfer of life from one system to another seems slightly more plausible. One intriguing mechanism suggests that, as a result of asteroid bombardment on an Earth-like planet, a fragment of rock enriched with microorganisms could be ejected. During collisions in interplanetary space, this fragment could break into smaller pieces, which could then further fragment upon encountering interplanetary dust. Once reduced to a critical size, around 1 micron, these particles could be easily carried away by stellar wind, which would rapidly expel them from the system. Importantly, the particle size would still be sufficient to protect microorganisms from harmful ultraviolet radiation. At the same time, it would allow them to escape relatively quickly from the system. Traveling through interstellar space, these particles could eventually become incorporated into a young protoplanetary disk, completing the journey of life from one star to another. Of course, all this is highly hypothetical, and astronomers are generally very cautious about the idea of interstellar panspermia. However, it is fascinating to think about this in the context of studying the Sun's relatives. A much more practical reason to search for and study our stellar siblings is to better understand the origin of our own star. The Sun is the most studied star in the universe. We've even managed to touch it. Yet, despite this, the location and environmental conditions in which it was born remain poorly understood. In fact, studying these could provide us with crucial clues to one of the most profound questions: where does life on our planet come from? So, we look forward to new discoveries of members of the Sun's parent cluster and studies of their planetary systems. After all, if we are to search for Earth's twin, it is better to do so in places similar in chemical composition and formation conditions. That's all for now. Thank you for your attention, thank you for your likes and comments, and see you in the next episode.